Morning, everybody. Stonehenge still works. Well, the order of the business today is so there's a bunch of pictures here. I wish I drew them smaller. Anyway, so what we're doing today is we're doing the difference. So we're doing the Q-difference equation in scalar variables. So there's no good way to capitalize Q difference, because if you apply large Q, big Q, capital Q, that means something else. So okay, this is an important topic, but I don't know how to capitalize it. Anyway, that's the topic for today. And so what would be so we so this is the Q difference equation, which this object is the fundamental solution for this. This is a fundamental solution. For this Q difference equation, and I recall this is really the sum over, this is here with sum over here with sum over all degrees. With the weight z to the degree. And so this is fundamental solution lies, it's an element in K equivariant, also localized, of X, or maybe endomorphisms of that. So endomorphisms K equivariant of X, it's also localized, and then it's has formal power series in Z. So this is and this is where we expand. This depends on which are they. So it depends on the choice. So this is as we discussed, this is an equation that serves, in fact, one equation that serves all birational models of X. Serves equation. The equation will be rational. Rational in X. In Z. And so serves all birational models. Also serves X flop. So there's some different birational model of X. Or if you're talking about a GIT quotient, means a different choice of stability condition in GIT quotient, and then this means where we expand in Z, that like, so let me turn off the chime. I'm glad people joining, but we'll have people join more discreetly. So this is where we expand. This depends. So this depends. This is what is this really? This is really this formal power series. This is the semigroup ring of the effective cone of H2XZ effective. So this is where we expand. What depends on which birational model we take, but this will be probably different solution correspond to different birational models. And the comparison between them is the monodromy, the Q difference equation. But anyway, first thing first, we have to discuss how we're going to describe, how we're going to determine what it is. Right? So the strategy. This is the strategy we already laid the foundation in from last time. And the strategy was that if I take the strategy says that this K series of X for different X form, for different X where we vary here. So let's say, let's for concreteness, and not only for concreteness, but actual the statement of the theorem. So we take, maybe X is an Nakajima variety. Corresponds to some dimension vector B and W, or we can also do abbreviate, consider the disjoint union over all V and VW. This is like a weight space, and the K theory of that is a representation. K of that is a module over a quantum group. And so this these guys form tensor category. So this K of M, if I take K, now we discussed many times, so if I take K of M V tensor K of M V prime, then there's a stable envelope map. So since it's a component of a fixed locus, this goes to the Km of V plus V prime. And this makes all the spaces into a structure which we discussed. It's like a tensor category. It's basically even slightly enriched, because in a tensor category you don't get this intermediate space, but anyway, it's like tensor category. And since this is the fixed point of a C star action, there is one more. Here we get one more recurrent parameter. Let's call it A. And so this is the fixed locus of A. Or maybe it's the case here, the fixed locus of A. And then since this operator is a fundamental solution, so this is a fundamental solution of a difference equation, the key difference equation in both. In both Z and A. So we get, therefore, this means we have a flat difference connection in both of these things. Right? Means this guy, well, in A we determine what it is. In A, we know that this is the QKZ. Right? So in this particular situation, it's the two tensor factors, and so this means you get operator of the form sub psi. Yes, the equation is psi of QA is Z tensor 1 times R1 to times R the matrix. This R matrix, the function of A times psi. Okay. And so it means, and I now claim that this commutation really determines, so this means this determines the Q difference equation, the connection in Z up to a scalar multiple right? Because suppose if I have two connections, two different operators in Z, the two connections in Z, they commute, but they both commute with the same connection in A. That means the difference between these two connections would just really commute with R matrices. And this is, and the general principle is, maybe I can summarize, so kind of maybe motto. Really, maybe I'll say it slightly incorrectly, but so that you can somehow memorable, says nothing commutes with matrices. Commute with our matrices. Maybe more except scalars, and moreover, so means our tensor category, means this tensor category has very few tensor automorphisms. So this is a general fact. If I have a quantum group, then it's unlike so this means very, so this means you for every, so if some collection of vector spaces, for every vector space you have to designate a map, which is like a connection matrix for us, and then they have to all respect our matrices. This means they have to be automorphs in this category, but you have to commute with that. All respect these maps. All these maps have to respect the stable envelope, means they have to commute with all our matrices, and there's nothing that commutes with all our matrices. This is slightly imprecise principle, but it's true, so it works. And so that says that this is if I give you a difference connection that commutes with our that commutes that up to scalar multiple, and that scalar multiple is actually kind of interesting. So this is, this is somebody wants a research problem in the area. This is interesting. It's really meaning research problem equals research problem. Because it's not stupid, this scalar, but anyway, somebody wants to investigate, even in cohomology. So this is maybe is there a question?
Yeah, maybe I'm conflating two different notions, but like when we were defining QKZ, we had these elements that commuted with R matrices as part of the ingredients, like part of the maximal torus of the quantum group.
Right.
Is that more?
Yeah, that is fine, but that's from the point of view of is a constant.
Okay.
Meaning right. So from our point of view, is a constant, because Z, our spaces are the weight spaces. So this is I remind, so up to scalar multiple in each weight space. So this is correct, right? So this is in each weight space. So it's true, our quantum group does have group-like elements, and those are the exactly elements in the maximal torus. And they are group-like, they commute with our matrices. But this means, but in their weight space, our actual axes are, their K series are not whole representation, they're weight space representation. And so this means K series of an actual M VW. There it's a constant. Okay, makes sense?
Thanks, yeah.
Sure. And it's an interesting research problem, even in cohomology. In cohomology, there's a way to say what it is more concretely, and I'll explain this. And so in cohomology, the commutation with our matrices, that's really so in cohomology. So this is the easy part, and if you're well, let me know if you need a copy of our book. It's finally published like last year. And I've been meaning to get a bunch of copies from the publisher. I'm sure they have none of them sold. So maybe anyway, if somebody wants a copy of that, I've been meaning to get them from the publisher. But anyway, so in cohomology, that is really easy. This QKZ, this is really easy. It's an easy consequence. So in case here it takes a while, but this is easy. Says that gives the quantum differential equation. So this gives the quantum differential equation of the Brownian connection. For X. So what does this guy look like? So a quantum differential equation. So this is what this is what this vertex function satisfies in cohomology. So that is it's a connection on. So this connection is a connection on a trivial bundle with fiber. The base is h upper 2 of X, which is also peak X tensor C, which is also the Lie algebra of this torus Z we were discussing. And the fiber is now instead of cohomology, K-theory is the cohomology. It's the Crane cohomology of X. And then here if I want to move in this base, maybe I have some directional lambda. So I have a vector field d by d lambda applies to z to the alpha, where alpha is, so that's a curve class. Remind you that the z this was an element in the semigroup ring of the effective cone. So elements there are z to the alpha. So that is, you pair lambda with alpha, and you take z to the alpha. That is how differential operators work. And so then the connection becomes. So then the connection in general, the Brownian connection, has the form d by d lambda minus the quantum product by the lambda. So that's the quantum product. And this concretely, for us, this quantum product takes the form what? Takes the form the classical product, cup product, plus, or maybe rather minus this parameter h bar, which is the weight of the symplectic form, This has to be operator of cohomological dimension 2. So if you multiply by lambda was an h upper 2, so this increases the cohomological dimension by 2, and so this is h bar. This is an h upper 2 equivariant of a point. So this is where it belongs. And now comes the interesting part. It's sum over all effective roots. And effective means, so these roots are the roots of the Lie algebra we constructed a long time ago. And then you pair, first thing you do, you pair your lambda with the root, which is okay. then you get a series which corresponds to, so root is a curve class, and so this means this is just multiple covers. So it means once you have a curve class, then you can cover it twice, 3 times, and so on and so forth. And for this computation, they all contribute the same. And so this means you have a z to the alpha plus z to the alpha 2 alpha plus z to the 3 alpha, and so on. And then you have some operator which is of homological degree 0. Maybe we denote it C alpha. So this is some Steinberg correspondence. So it's size to the homological degree, so middle dimensional, so it's Lagrangian Steinberg correspondence, and you can phrase it in terms of the Lie algebra. We have, so this means, recall we had a Lie algebra. This is from the classical R matrix. And this had a Cartan decomposition, had this Cartan subalgebra. This acts by linear functions of V and W, or you can also think that this is this Cartan. You can think of this. What is V? V is the same as px tensor C plus center. So this W is central. So this is that. Plus sum over all roots, G alpha. And then a root is, so this non-zero, I mean, roots is by definition non-zero. So root is effective. Each represents a curve class, and so this is root is effective. Well, it's easy to say. It's just this is if and only if you take dot product. So this is the stability condition. Usually people refer to stability condition, e.g., usually very often people take all ones or all minus ones, and so then it's means a positive root. And then the C alpha. Well, this is the Casimir element in G minus alpha G alpha. So the image of the canonical tensor, these are G alpha and G minus alpha are dual with respect to so G alpha dual is G minus alpha with respect to canonical bilinear form. So this is the Casimir element then. And while we're at the topic, then also one can say, what is lambda? No, this is the Yangian deformation of lambda times t, and this would be in H t, right? So lambda was an element here. So this is my Cartan subalgebra. And so then in the Yangian, you get, this is deformation of polynomial functions with values in my Lie algebras. In particular, there's a linear t times lambda. And so that's, this is some like an older brother of, so this is kind of next generation. Kind of older brother of that. Or who's older, who's younger, that's for you to decide, but this is like it's like the next, this is, if this is if this is the up or down quark, this is the strange or the charmed quark. So, and then there's a top or bottom, and then there's no more names after that. So this is and now if you look at this formula, so it's a good formula. And this is, if you look in our book with Zavesh, then it's very easy to. I mean, this formula is an easy consequence of the fact that this has to commute with QKZ. But it's harder to, in K theory it's harder. So so in K theory the main differences. K theory means, of course, first difference, or maybe with first or second, I'll just take bullet points. So of course sums become product. Of course, everybody accepts this. If I had Yang and something associated to additive group, and the quantum group, the full UQ, or rather UH bar, this is something associated with multiplicative group. So where you previously had an infinite sum, now we have an infinite product. Right. Well, we'll come back. Sorry, there's one point I forgot to make. I'll make it. And then roots of G. Well, this would be promoted to roots of G hat. So that is to say G tensor polynomials. Well, let's say within. You don't need the complex coefficients here, but well, whatever. Let's take complex coefficients. We want like rational coefficients. It doesn't really matter. It's an integral. It's really integral form. So whatever you have. I'll just put rational coefficients. So so that's and then and everything except everything is best. So everything is best phrased in terms of some notion maybe called dynamic group. And so I'll explain what this thing is. And this is already we saw an example of that. We saw in fact 2 examples of that last time. And but it's okay. So this is I'll start from the beginning. And so this is
so
you start. Sure.
So about the cohomological case, yeah, first of all, so the QKZ, isn't it supposed to be in covariant variables, or?
Yeah, it's in the covariant variables.
But those are the curves classes, which are the base of the bundle, no? The connection.
No, this is so. So this is the. So in this connection here, you can formally write this in the covariant H2, but that really doesn't. This really makes no sense there. So this is some difference. So this in K theory we have Q difference connection commuting with a Q difference connection, and in the homology case we have a differential equation commuting with a difference connection. So that's
and also told that there is some constant problem. So the equation is determined from commutation by some constant, but this equation looks completely.
Oh, right, exactly. Yeah. So thanks, Konstantin. Yeah, that's right. So this is plus a constant. Yeah. So the analog of that. Yeah, super. Thanks. So plus a constant. Yeah. Plus, maybe this plus is too small. Let's try a bigger plus. Plus a constant. It's very fitting that Konstantin should bring a constant up. So that's very well. Anyway. So constant. So where is that constant is determined by? the constant is determined by. So this is, so you can easy to say in cohomology. There's a way to, no, I don't want that. In cohomology, so the constant. So maybe I'll. So let me write it here. So in cohomology, the constant is determined by the condition that if I take the quantum product with one it's an element in, so this is in, I need more space here. This one is an element in H0 of X. This is really identity in cohomology. That is lambda.
I see.
And so this means purely quantum, means the purely quantum IE, purely quantum part. Or quantum correction, kill one. Kill one. Okay, that's easier said than done, because to say what this one is in terms of, so what this one is in terms of quantum group, this is some kind of weird corrector for quantum group. Vector. You can say what somehow discuss what how to actually describe one as an element in the module. I mean, cosmologically, it's clear what is one, but if I want a representational quantum group, then it's not so clear how to describe one. I mean, it's clear, but it's not so easy. And then moreover, once you describe it, then you have to compute some number. There's some number, and this number is usually 0, but sometimes not, and sometimes very often it's 0. And this has to do with the fact that there's some phenomenon called large framing vanishing, which we'll discuss maybe in the next lecture or the lecture after. But says in some stable range this number is 0, but in some original some kind of early cases that number is not 0. So if you take like e.g., so this is example. If you take MR, the instantaneous, so rank R instantaneous, then this number vanishes. This constant, this extra constant vanishes. Equals 0 for rank bigger than 1. If in rank 1 there's some correction, and all higher rank is nothing. And this is the general principle that in some stable range there's nothing, but in some lower cases you have to compute. So okay, now coming back, and like I said, this is maybe Konstantin, maybe I'll finish what I say, in that it's not there is the analog, the k-theoretic analog of the statement that quantum correction will kill one. It's not exactly 100% has been figured out, and so first of all, this whole computation will be it's harder in k-theory, but also the fact that the statement that quantum correction will kill one, and that this statement is strictly speaking, that statement is not true in k-theory. They kill something else, and this is you have to be a little bit more specific about that. Because what does it mean one? One means a structure sheaf in k-theory, and in fact, you shouldn't take the structure sheaf. You should take some line bundle and so on and so forth. So that's now. What do you want to ask, Konstantin?
Yeah, basically that answered my question.
Yeah. Okay. So now this dynamically group point. What did we? yeah, what was that? We already saw it last time. Where did I have this picture here? I can copy this picture here, or maybe not this picture. Maybe let me copy this picture. I made too many pictures for this talk. I don't know. Instead of preparing the talk, I just went for drawing the pictures. We're probably not going to use them. I mean, I'm quite certain we're not going to use them all. So so we start with, so this is, first ingredient is that you have either some arrangement of hyperplanes, so it's either periodic arrangement of hyperplanes, of rational hyperplanes, or since it's periodic, you can think it happens in fact on the torus, and so this is more. So this is also arrangement of codimension 1, or translate, arrangement of translate. Maybe I don't need arrangement for that. It just says union of translates of codimension equal 1 sub varieties, I say, in an abelian variety. You can also do it in a torus. So we think of this. We will think of this as sitting in a torus. We'll think of this today. We'll take both. So maybe there's a torus. Now let me call the torus for the thing we discussed last time. So maybe there's a torus. Maybe this picture is in the Lie algebra of some torus A, right? And then there's then you also have the corresponding subtora in A, and then you have the elliptic version. Just write like the A equivalent elliptic homology of a point. So this, and this means here I have a hyperplanes of the form some root alpha plus dot plus some number n equals 0. So this is where alpha is some root. And this is then here I mean I have equation of the form A or maybe X. I'll just maybe call this root beta. Beta. So it will be A to the beta Q to the N equals 1. And then this means you descend. Same expression here. Right. And now what do I want? I want for every wall of this arrangement, I'd like for every wall I'd like an operator. So if I have a wall, then I'd like an operator, maybe B wall. And so this B wall, well, first of all, it depends on some variable in my torus. It depends only on the variable which is just going to vanish there. So it's this variable. And it acts in some space. So it's antimorphism. Vector space. Some, endomorphism of some free module or some ring, whatever, say vector space. And what would I like? I like two properties. I'd like that this is satisfies the condition that if I go, so there's really two relations. Is that if I have what do I want? So maybe all right, as I satisfy braid relation. So what's a braid relation? Braid relation is if I go around any closed loop, I have to multiply all these operators. So if I go around a closed loop, I multiply all these operators. I get one. And an example of this, so example of that is of this relation, e.g. Young-Baxter with spectral parameter. So this is what's a Young-Baxter with spectral parameter, where you have three lines like this, and then the corresponding equations are W1 or maybe whatever U1. So this is in a torus where I have U1 over U2 equals 1, and then well, just logarithmic 1 just means this vanishes there. Then you have U2 over U3, and then you have U1 over U3. And then Young-Baxter says that if I multiply all these matrices around, and I get 1. That's one example. That's one thing. And then additionally, this one relation. Additionally, I'd like to want the automorphisms of my lattice, automorphisms of my arrangement. And this automorphisms of my arrangement, they always include the lattice, since I take my arrangement to be periodic. And then they operate on this B of V. And they operate, well, how would they operate? This is if I take my B of V, and now so maybe I have an automorphism, maybe call it, what shall we call it? Maybe tau, since we're thinking about translations. And then how do I act on function? Inside here, I put the tau inverse of my variable A. Right? That, well, maybe the easiest, of course, if it were just act on the label, right? Because an automorphism will take a wall to the wall. So that, of course, maybe this would be the easiest, but that's not what happens in nature. And instead, you get maybe also conjugation, some operator, call it O of tau, because O of tau inverse. So that's another thing I want. And so what would be what would be that? What would be an example of that? An example of that is maybe let me put some no, I wanted to do show appreciation for this formula. And so, for instance, what would be an example of that? An example of that is if I take this arrangement here. Let me see if I can copy it. No, but not so easy. So, okay, let's see if we can. Come on, arrangement. Let's copy. Copy. And then paste. Oh no. Well, bear with me. This is a comic relief. Now we will eventually get to what we want. so this arrangement here, this has, in addition to lattice automorphism, it also has, so this automorphism here, automorphisms of that arrangement, that's a group, well, here it's S3, or the general Sn cross Zn, Z3, or well, Z2, let's say. And this is not exactly the affine Weyl group. It contains the Weyl group, the affine Weyl group of GL, what 3 head? Because in affine, it also has the outer. So the difference between them is the outer automorphism of the Dynkin diagram. So if I have the outer automorphism of the Dynkin diagram, there's a rotation by 1, and that rotation by 1 is the rotation by 1 of any of that triangles. And so then last time we constructed an action of that. Remember, we had an action. This was acting by Q difference operators last time. Where this part here was acting by QKZ. And so this is how did this construction go? Maybe in this language we're discussing here. So this means, well, here we had, of course, here we had the kind of the R matrix R1, 2. Here we had the R matrix R2, 3, or maybe R check because it also permutes the coordinates. but this guy here, the affine, let's say this is the origin here. This is the affine wall. Affine wall. And what the affine wall corresponds to? The affine wall corresponds to the fact that when we had the cylinders, I have some sort of autocorrection here going on. It's interesting. I don't know how to. I had no intention to turning it on, but this seems to be working. Anyway, so what happens in the affine wall? In the affine wall, it's you have the 1 and the 3rd will exchange some maybe. So the 1 and the 3rd will exchange their places behind the back. So one will come back here, and the 3 will come back there. Well, maybe this is not the best drawing, but anyway, here, somewhere around here, they're behind my back. They exchange places, and then in particular, they were crossing this seam. That seam had this operator Z in it. This contains Z. And so that Z is that that Z has to do with the Z has to do with the conjugation. So it's not just if I want there is an automorphism of the affine arrangement that takes I don't know, let's say any of these walls to the affine wall. But when I don't get just the R matrix, I get the R matrix with that Z. So that's what we saw. And then once we have the structure, then this structure, gives rise to a Q difference connection. Because really I take my lattice inside the automorphisms. And how does the lattice act? I recall the hyperplanes were of the form. So this, where was it? Yeah, the hyperplanes were of the form something to the power. The affine part of the hyperplane that was that contains Q. So this is so if I have a lattice means this really act by Q difference up. So it mean when B W of T inverse of T inverse A, this is where T inverse, if this is a translation by lambda in my lattice, this means that this is BW of Q to the minus, well, what does it mean? It really, this means, well, just really means you translate by Q to the minus lambda times A. Because the difference translation by one means Q, right? So this is what? And then in fact, I can write formal solution to my Q difference equation. Namely, I take my take this picture. Well, maybe I have already picture with the path here. So this part I don't need drawing now, and this part I'll have to make it blue also. Oh no. So how do I write? Sorry for my kind of lack of proficiency in drawing this picture. So this means if I choose a path that goes to infinity, oh no, I choose a path that goes to infinity. And goes to infinity means it crosses every if it crosses every line sufficiently deep in some direction. It's not like it runs parallel to some line. So we'll discuss what this means. And then we take, and then from this, we just write, oh no. Okay, maybe this is the part. Maybe this part I want to undo. Right. So from this we just take a product along this path along all walls in the order across them. And so maybe this is wall 1, wall 2, wall 3, so forth. So it means you take BV1, BV2, BV3, so on. So then this object satisfies a Q difference equation. So satisfies, this satisfies. This is just a formal consequence of the rules I wrote down. This satisfies an equation, and it doesn't matter which path I choose. So this is independent of the path really, because my so if I choose a different path, then by the rules of the group, maybe that's not the best choice of the color. So if I chosen a different path, then by the rules of my groupoid, nothing can really happen. So I'm free to choose it any way I like. Then that satisfies Q difference equation. Of the form that if I take this operator, this so maybe call it psi, call this function psi, and I believe so. Now I have to look at my notes, because of course I believe I wrote down the equation correctly, but then of course you can, so I believe that if you take this kind of action of this tau lambda on psi, what you're gonna get is, and then you take your operator of lambda, that is of lambda times a product of BW1, so finite product times psi. Maybe this should be red also. So this is my operator here. Call it M lambda. And what is this product? This product is the product. This is the product along a path that goes from wherever I had it defined. So I had my circle somewhere here, and now I'm go to the circle which is that same circle, but now I translate it by. So this is my, this is my original circle, but now translated by call it green, translated by lambda, and then I choose a path that joins them, and along this path I multiply all the matrices I get. Right. So that's the equation. It's a formal consequence of what I wrote down. And last time we had, last time at the very end we discussed conjecture / project by Yasha. Yasha is still not on the call to update us on the progress on this. Okay, and Andrei. Smirnov is enough. That this is if I just take a different general. So this is what it says, is that the general Q difference equation equations for invariant variables have this form, where sits what sits on the wall. If I have a wall, so if I have a wall means I have some means on the wall I have like the fixed locus of the wall, and then here which is larger. So then here I have the fixed locus of my whole torus. Here I have my fixed locus on the whole torus, and this is larger. And so then you have going from here to here. Well, one has an R matrix. The R matrix for xw decorated by z like in QKZ. And so this is, and then also with the shift of Q. Because the R matrix doesn't depend on Q, but this has to depend on some. So if I have an element in the torus, if I look for those elements of the torus that have extra fixed points, they form an arrangement just like one. It's like one, so it means my arrangement. This is the elements in the torus such that the fixed loci are not equal to the fixed loci of the whole torus. It's an arrangement of translates of tori, just like I want. And this is that there is a natural wall operator, the R matrices for the corresponding fixed loci. And what should be is that. But now so one day we will hear from Yasha and Andrei into how their progress. So what today we instead would do. Today we're torus something else. Torus is this torus Z, which is here called peak X tensor C star. And then the arrangement, these are slopes for which stable envelopes jump. So now a reminder. I myself forget what's forget things we discussed like in summer. So you probably also forgot, but a reminder. So stable envelopes in elliptical homology. In elliptical homology, there are sections of some bundle, which is something like theta over polarization times something of degree 0. Some line bundle on a abelian variety. Now on on equivalent elliptic homology of X. Now, so this is a union. Equivalent elliptic homology we discussed. This is like a union of abelian variety. So this is a union of abelian variety. Each of the edges of the abelian variety is the form T modulo Q to the co-character. Roughly, right? So now if we send Q to 0, this abelian variety. So what's happened with the abelian variety if the what happens with the abelian variety if the modulus goes to 0? Well, this will correspond to periodic gluing of toric varieties now. So this is okay. We can it's fun to talk about this, but requires it requires a whole bunch of notation. Maybe we'll skip it for now. It's of the same. It's a construction of the same general ilk as we discussed here. So some kind of periodic thing, but and then they correspond to K-theory, to spectra. They assemble into the spectra of a covariant K-theory of all possible fixed points of all possible subtori. So whatever T, where T is, this is the union. You take all possible. So it's just like we discussed here. So you have all possible fixed points of all possible elements in your torus. Then you'll have not just in a elliptical homology, you get not just K-theory from elliptical homology, you get not just K-theory of X, but also you get K-theory of all fixed law sets. So this is this fun thing, and you can read in that I mean, in the sequence of papers like 1 and 2, you can read in the part 1. You can read about it. It's combinatorial statement of the same general thing that we're discussing here. And so in particular, in here, of course, as the in here is also the spec of K0 of X corresponding to the identity. So this corresponds to T being equal to 1. Sit there right in the middle of that. And then here you get, so this is this means in stable envelope in K theory. Well, there are now polynomials with being a section of some line bundle is now translated. Now we're in K theory. K theory is a spectrum of K theory. That's an affine algebraic variety. So there's no, and with no, I mean, not the reason that's fine. With the variety doesn't have an interesting line bundle, but has analog of line bundle is the notion of degree. So this is with Newton polygon. Of the form, you take the exterior algebra, same as exterior algebra of polarization, Newton polygon, plus, so that's the analog of being the theta function of polarization, plus like this really shift. And that shift is the analog, so you can do additive shift, and this is the this additive shift comes from degree 0 here. And then the degree 0 line bundles over here, they were coming from the interesting degree 0 line bundle on elliptic homology. We were constructing from just peak X. Well, we're taking odd times elliptic curve. But now this shift is really by peak X odd times R. Right? And so this is I have a picture of that somewhere, I guess here. Yeah. So maybe. That means here you have the the Newton polygon of polarization, pictorial algebra of polarization, and here's the same plus shift. And as you do this, then this means the actual lattice points you get would be the lattice points. The actual lattice points are locally constant in this shift, and they change as you cross some walls. So you get walls from this picture. You get walls in sort of periodic. Get walls in peak x tensor r, because this is where this shift was, and they're invariant under the action of peak x. Because this action of peak x is really multiplied. So this action, this is the stable envelope. So if I have a line bundle in here, it changes. It's really by multiplication by tensor product by that. So if I ask for this stable levels of some elements in K theory, and if I specify them by what their degree is, and I take that degree and move it by a line bundle, then of course the corresponding element in the K theory is just multiplied by the line bundle, you'd be done, right? So this guy acts here, and so then you can define. So I presume many of you have seen this before, but I'm not assuming that, so I'm trying to explain. And so then when you can define, so these are the walls. So what should those sit on the wall? On the wall should sit, so again, we go back to my picture here. Oh no, that was too. Oh no. No, I can't erase this part. Let's see. Okay, like that. So what will sit on the wall is you have. So this is now in peak x tensor r. So for every one of the slopes, so this would be maybe some element that's called the slope. Slope denoted f. And so for every slope s and s prime, we can define, we have each one of them gives a stable envelope. And so then we can define the wall R matrix. So wall R matrix. Maybe this is the slope. So maybe if I crossing it this way, this means I take the stable envelope. This is not the operator yet. So this is not, to avoid this is not BW yet. BW we need to, it's not in the right variables, and so this is, we'll get there. So associated to this, but there's a stable envelope at this slope here, and then you compose with the stable envelope of the different slope inverse. And then, so this is this. So what are the properties of this? First property, it satisfies Yang-Baxter equation. Okay, that's one thing. Second thing depends on the spectral variable. In a trivial way. Trivial way means if I have so the R matrix has some spectral variable, means maybe spectral variable, I don't know what we call it, called maybe A. Trivial way means A to some monomial, means monomial. You agree? So in that sense, it defines a quantum group which is not so defines. So means defines UH bar of G wall, which is not a loop group. The quantum loop groups, the R matrix is really depend on spectral variable, and here will depend on the dependence. It just goes out, washes out at some overall conjugation. It's not an interesting operator. So it's really just a. And then moreover, like the next property is that if I interested in the R matrix for the whole, so where's my picture here? You can see it in two things in my background here. So actually I need them both. So I'll try to copy them both here. I apologize. So then not in logical order, maybe. In logical order, you for some. Oh, okay, maybe I'll say it in logical order. In logical order is that if you want the R matrix, the old R matrix. So this was the next bullet point. The old R matrix, which we discussed, R matrix corresponds to changing the attracting and repelling directions. So has Мишел Крошкин to story type factorization. Meaning that if I say means what? So what is the old R matrix? The old R matrix is you fix the slope, and then you change the, let's say you change the, let's say take attracting to the, in the picture you take some attracting direction and you send it to maybe, let's say you take some attracting direction, take it the opposite. So this means slope, and this means a choice of attracting repelling directions. And so this has a factorization where first you choose a path that goes to infinity, and then you choose a path that comes from the minus infinity, like like I wrote here. So first there is a term which is it goes from your slope, you go to infinity, and you multiply now the R matrices where you fix the attracting direction, but you change the slope to new slope. Means you have there's a slope, there's a next slope, there's a third slope, and so forth. So you just change the slopes, and then you have some R infinity, and that's an explicit product. Explicit product of Q gamma functions. It's not how I spell gamma in English. I'll just, if I write product of Q gamma, it'll be like that. And then you come from infinity. And then, so here, this R metric changes. So this goes from 1 infinity to minus infinity, and then from the cone to the minus cone. And then here you come back. Again, you change the slope, you're at the minus cone, and then you change the slope. Right? So you choose. So this is the choice of this path. Choice of this path is the analogous. Is like is like the choice of factorization of the longest element in Weil group. So if you look in like Lustig, then various state. Well, if you should look at Lustig, but when you look at Lustig, then there'll be many statements about quantum group that require a choice of factorization into the longest element in the Weil group. The analogous statement in Skoroshkin-Tolstoy is the choice of ordering of all possible routes, but what really is a choice of a path that gonna do this. And then it also means, so this factorization also means that all of these wall algebras are really subset in your UH bar. And so these are kind of root subalgebra. So the picture may be familiar to you, is something many to you is a picture like that. So this is a picture of, well, UH bar of G L1 hat. Here the Lie algebra G is GL1 hat. Its roots are the integers n, but then the corresponding walls, so this is beta set of beta that is just set. And then here if we look at the corresponding hyperplane, we're looking beta times x plus n is an integer. So these are so beta times x is an integer. These are the hyperplanes. This is my arrangement, and the arrangement is going to be like what? So there'll be, of course, all integers, but also then our numbers with denominator 1/2, then numbers with denominator 1/3, and so on and so forth. So these are all, that's my and so on and so forth. So this would be, these are the this is my arrangement in px. And then the operators, so this is, you can also, so the fact that there's infinitely many of those, you can ask, well, I mean, we already saw this expression in the homology case, and the homology was also an infinite sum, but of course, all but finitely many, many Euler matrices act trivially, or matrices trivially in K theory. K theory of any given. This is fixed. So when we fix, then my arrangement R is all fractions of the form A over B, where B is at most N. So that's my arrangement. Everybody else, this is also exactly the same as it was in the formula. The formula before, there was in principle infinitely many operators, but they all first they lowered dimension by. So this is maybe okay. Maybe I'll correct it in the note. Add this note in the note. And so then the corresponding subalgebras, well, to be all. There will be different sub. So this would be like this horizontal subalgebra. That would be U H bar at slope 0. This would be U H bar at slope 1/3. Then there's U H bar. This is the slope 1/2, and so on. So each one of them is some subalgebra. And those guys correspond to the infinite slope. This has to do. This is the R infinity in hierarchical Tolstoy factorization. And now we come to the conclusion. Is that so? Now we come back to where we started, not to what we. So now we have for every wall, we have, well, this gives us this wall subalgebra. And and this is or G wall, sorry. Where this G wall, it's whatever was before, this is the rank one. The algebra. Means it's Cartan-Torus is really one-dimensional, just because that's the only. This is the those are well. Anyway, maybe you think about it. Since we're in overtime, maybe I'll skip this explanation. So then for that, there's a, as I said, write a QKZ for this. So is not a difference equation. It's just a linear equation because the difference that shifts the loop. So difference the variables Q difference part comes from loop rotation. And so if you think, what's a QKZ? Well, QKZ, so what does it mean to have an evaluation representation at some point? It means you pre-compose with an automorphism, which is a loop rotation. So we don't have that automorphism now. We do have it, but it's trivial. And so then instead of difference equation, you just get you get an equation of the form something like so. This means instead of psi, which is solution of QKZ, we look for this is traditional denoted J, and J solves the equation that if some Z tensor 1, so to speak, R matrix acting on J is J then Z tensor 1, and then the R matrix at 0, which is that part is just H bar to some power. So like I said, the R matrix formally has a spectral variable, but that spectral variable can be scaled away. So this becomes just the diagonal part. This is the diagonal part of the R matrix. And then from this J, so J depends on that. You write something universal. So this is by a universal formula. You write some expression BW of Z. This is called dynamical reflection. And so what does it mean universal? Universal means only involves tensors, the canonical tensors in a Hopf algebra, namely multiplication and antipode. In Hopf algebra. And this is, I think, something like that has the form BW of Z. I believe it's so it's been a while since I was on top of this formula, but I think it's that you take multiplication of one tensor antipode, and then you put T, and then to one inverse, something like that. But the way to check it is this: since this is universal, and universal in particular should hold for SL2. In the case of SL2, so in which case we should get the quantum Weil group. Or dynamics, or not the quantum, dynamical Weil group. Dynamical Weil group of Okounkov and Barchenko. Well, they also have concrete formulas for their they also have concrete formulas for their dynamical Weil group, but also have an abstract. I mean, if you have an abstract formula in particular, should be held there. So that's now there's a theorem of Smirnov and I. This connection. This, maybe call it dynamical connection. Oh, maybe this is a dynamical groupoid. So first we have to prove it satisfies This is a dynamically groupoid. And it gives the Q difference equation for Nakajawa varieties. Right. And so I'm going to say one word about how you prove it. So of course it takes like 100 pages to prove it, but the the main idea is that you have, what do we have? We have this seems to be the most popular picture of the day. So this, oh no. I apologize. I'd really like to complete this discussion today rather than to have a carryover for next time. So what's the main idea? So that the main idea is that you have a slope, you have some slope, and you have some slope prime. And then we have, means corresponding to that slope, means we have QKZ at slopes S and S prime. So for this too, so these are variables. So these are the variables. This is a parameter. In the R matrix. And so this, as this parameter changes, you have two different connections. And so the idea would be that instead of trying something that commutes with a given connection, let's find an operator that intertwines. So the wall operator basically intertwines, more or less, with the usual factor that's kind of intertwines. So if you have a wall operator that intertwines the two, then of course, what's going to happen if you go by a whole Picard, then those two corresponding QKZ would be the same. So they just conjugate. So the stable envelopes differing by a whole Picard element, they just differ by a twist by a line bundle. So the corresponding QKZ will not be different. And so it means if I go the length of the way, then what will happen is that I get, well, with all the twists, I get exactly the connection that will commute with QKZ. So and then like I said at the beginning, then there's other part of the argument that says that nothing commutes with QKZ. All right, so I'm sorry for going over time. So this questions.
I have a question.
Sure.
So we know there's a central charge map from the classical equilibrium case theory to solutions to quantum differential equation, and analytic continuation of solutions of quantum differential equation correspond to, under this map, Fourier-Mackay transformation of the equilibrium case theory. Is there an analog of like a map from classical equilibrium case theory to solutions of quantum difference equation?
Right. So that's an excellent question. Thank you, Melissa. So then you can. So these are also. So these are guys. So this same picture has to do, well, not exactly the same, but this picture has to do with also has to do with singularities of both quantum differential equation and quantum difference equation. So for instance, if I look at the for instance, pick when I take x to be, for instance, e.g. takes to x to be the Hilbert single points, and these are the singularities. These are the singularities z to the power b equals 1. This is the union. So this is the singularities for z. You get your z. The torus z is just one-dimensional. C star. And here the singularities are the union from b less or equal than n b roots of 1. And so then in here you can ask, what about, so this is, try to draw a picture. So this is my unit circle in different color. So there's maybe, -1, then cube, then 4, and so on, so on, so forth. And so then you can ask, what about actually like really the monodromy around a slope? So you have a slope here, maybe slope is 1/4. What's the monodromy about that? Now it's the monodromy. So you have the differential equation. You have the Q-difference equation. So this differential equation in Z, Q-difference equation in Z, and so somewhere between them sits this monodromy. Since the monodromy in Z, since it's a monodromy of the quantum, it's a differential equation in Z, that has no Z. No Z in here. And the actual these operators of the monodromy are it's one, if you think of a differential equation as being very, very degenerate thing from difference equation, monodromy is less degenerate. And then here this loop somehow going is given by this wall operators, but now in this wall operators you put 0. So it means you take Z to be or infinity, sorry, infinity. The way I define it, we put infinity. You bet this Z variables called infinity. And more generally, if you have this kind of dynamical groupoid, then it has some wall operator depending on Z. And then in that wall operator, you can, out of this wall operator, you can make two different kind of overcrossing and undercrossing operators, which would be, this would be BW of infinity, and this BW of 0. In our case, the way I wrote them down, if you go kind of the undercrossing, you experience no change because there's no singularities there. And if you go the overcrossing, you get exactly the monodromy. And so now, and this is proven. It's proven by its exact argument. By exact same argument. Based on nothing commute. with R matrices philosophy. And now, when you say about we know that it's given by some Fourier-Mukai transform, I'm not sure what you're referring to, because this is known maybe some toric varieties or things like this. In general, it's, I don't know. I mean, I don't know if you have a similar way to, easy way to prove it, but this is really, this stuff is really, yeah. So this guy here really is. So it can, you know, that's there is a categorical version of that. And this links with this sort of Bezrukovnikov collision quantization, which is now, this is now a whole different topic, which I'm not, because I mean, late in the overtime is certainly not the Bezrukovnikov collision. Late in the overtime, it's so quantization ideas. I don't want to go into that, but it is possible to prove that in fact there are these derived equivalences that categorify this maps, but I'm not aware of any simple proofs for that. So maybe if so this it is very related to what you say, Melissa, but I think, and it's proven in the way the proof I know is, again, you construct some kind of categorical stable envelope, and you prove they all commute somehow correctly, and then you conclude that nothing commutes with the R matrices, you're done. Yeah, that's the best I can mean. And then of course you can take this argument and then you can continue it. You can take the monodromy to difference equation, but that'll be a topic for a different lecture. Sorry, Melissa, did I answer your question?
Thank you. That's very helpful. Thank you.
Sorry, I'll be happy to talk more about it. Yeah. Other questions?
Do you have any examples of what J looks like or how it differs from the R?
Yeah. So yes. Yes, of course. So what is J? J for SL2C. Eisenkopf-Rodchenko, and other people who wrote about dynamical Weyl group. I think this dynamical Weyl group in application is a really good paper to read. For GL1 hat, this is the part. This is the part we need most. Right? Because it's the well, for the Hilbert scheme of points. For Hilbert C2N, it's actually all roots. So this is what's going to be which root subalgebra we're going to see. That depends on depends on like the north square of the root or something like that. And so for the Hilbert scheme, they all these roots are all have norm 0. So we're all going to hit GL1 hat, and then and so that the GL1 hat, this is direct sum of Heisenberg. So and goes from, so there's a countable many Heisenberg subalgebra, and so with some modules of centers identified, and so it's enough to write it for Heisenberg. And so for Heisenberg, if I saw what's a Heisenberg? Heisenberg is something like so you have an algebra generated. It's an algebra generated by E, F, K, and maybe H bar, subject to the relations that well, the commutation relations are follow from the following representation. I can take H to be H bar to the power X d by dx, and then K to be H bar E to be X and F to be minus D by dx. And they co-multiply. So this is the usual Heisenberg. So except when you have a Cartan, you exponentiate it. And the co-multiplications are of the kind that that the co-product of K is group-like. H bar, well, H bar is group-like clearly. I mean, this is just it's a parameter of deformation. And then sorry, not group-like. It's a variable. And then the co-product of where do I have? I'm not trying to find in my notes the formula for the co-product. Where was it? Hold on, one sec. Be here. Yeah. So the co-product of E is E tensor 1 plus K inverse tensor E. Then the co-product of F is F tensor K plus 1 tensor F. And then finally J with this formula. J is the ordinary exponential. So this means there's no Q exponential. And the reason there's no Q, not exponential Q square, because, or H bar square, this is because because the root, that square for SL2, because this 2, what is that's the alpha, right? And our roots are isotropic, so you get ordinary exponential. And then you get, I believe this is correct. So this is that. Just copying from my notes, I believe I wrote it correctly. It's so in other words, it is for SL2, except it's easier, it's simpler.
Thanks.
Sure. More questions?
Sorry, I realize that I don't understand the argument that nothing commutes with the matrix. So you said that we need to fix the weight, but in principle, if the corresponding weight space is not one-dimensional, then any operator acting here belongs to quantum group.
Say it again.
If the corresponding weight space is not one-dimensional, then I mean, if you have a irreducible representation, then any operator acting on the representation belongs to the image of the algebra. And if the space is not one-dimensional, then in principle, any operator belongs to the image of the quantum group. So we can have something. Looks like we can have something.
No, but you see, what does it mean? You have some operator, but for it to commute to the R matrix, this operator has to be group-like. Or basically it has to be group-like if you're looking for, because I mean the co-product is not co-commuted, right? So the co-product knows what it means to be commute with R matrices. It means the co-product of your particular element, how miraculous it turned out to be symmetric. But that is possible for group-like elements, but very few of those, namely just the torus. And how do you prove that nothing commutes with the R matrices? Well, if it commutes with the R matrices, then it's first of all commutes with like the vacuum matrix elements with the R matrices, and those already generate the classical K theory. That's a maximal commutative subgroup. So that means if anything commutes with the with multiplication is by classical K theory, there will be some element in that element itself. So you're asking for some to give you some element in K theory of X, which co-multiplies in a symmetric way, and there's none such except the only possibility is you take some variable and you raise it to the power dimension. That's the only thing that works.
Thank you.
Sure. I really appreciate you all sticking around. I'm hoping to wrap it up in maybe a lecture or two, and so then we can at least, like I said, you're sticking around and listening to all this is greatly appreciated. I wish everybody you know, all the best. I'll see you in a week. That's let's see, where did I turn this off?